Today is August 11th, 2015. Here's something I'll link to the bottom of the page. This was a study on V374 Pegasi. I'm not too sure how to pronounce that, to be honest with you. It's a red dwarf. Surface temperature of 2900 Celsius, so it's a lot cooler than the sun, which is roughly 5,880 Celsius. But it's strange because the global magnetic field strength is 1,000 times stronger than the sun's global magnetic field. You'd think naturally that something as big and as massive as the sun would have a huge magnetic field that's global. Very, very strong global magnetic field. But as it turns out, it doesn't. At least when you put in red dwarfs, they actually have much stronger global magnetic fields. Their global magnetic fields rival the sunspot's strengths on the sun. And three things this signals, according to stellar metamorphosis. It signals that the sun, since it has no global magnetic field, it signals that there's an absence of a core because there is no large-scale convection. For there to be large-scale convection in its internal regions, there has to be something to convect against. There is nothing in there to allow for the convection to move against. It just goes wherever. There's no coherent direction. As well, it signals youth. If you have a core being developed in a red dwarf, that means it's much older than the sun, because the sun doesn't even have a core yet. Now, on a brown dwarf, this brown dwarf, J 18353 plus 3259545, that's the name of a brown dwarf. I'm just going to ignore that name. I'm going to call it money. We're going to call that money. Because that's how much money I expect to see in my bank account one day. Yes, and if you do math, it's 183 trillion. I highly doubt that's going to happen, though. You have a brown dwarf that has convective cells in the core, and it retains its global magnetic field as it cools, and all the materials combining, making molecules and such, and sorting out based off of its ionization potential and its mass, both as well as other factors involved, based, what elements it combines with and all that stuff. But one important idea that I want to get across, because I know you're going to see a lot of this in a lot of publications online and various other propaganda, is that the brown dwarf, it's not a failed star. It failed doing fusion. No, it's not a failed star. It's an evolved, intermediately aged star. A brown dwarf is quite a bit older than a red dwarf, which is also quite a bit older than a sun-like star. It's a lot cooler, radiates mostly in the infrared, and its magnetic field strength, global magnetic field strength, is also really, really strong still, on the order of 2 to 3 kilogauss. And two very important notes on that is that the magnetosphere is the big, well, it's not exactly a sphere, but I mean it's that regions where the magnetic field reaches out to. It stays in place as a global magnetosphere once the star passes into red dwarf stages. So it reaches a point to where in the red dwarf stage, the field becomes global, becomes really strong as the core is being developed, giving direction for the convection. As well, it stays there, and it shrinks as the star evolves. So the star adopts the global magnetic field, and it just stays there. It only weakens alongside the weakening of the radiation belt. So basically, as the star evolves, as well, the magnetic field will shrink considerably as the star's convective motions in its interior slows down considerably, and less material can convect. As well, two main ideas. I wrote them at the very bottom. Hopefully you can see this. I have problems adjusting the iPhone sometimes. But if there's no core in a star, the surface magnetic fields will always dominate the star's magnetic activity, meaning sunspots will be apparent. If there is a core, the global magnetic fields will dominate, meaning it gives something to convect against, as well as being that it's iron nickel that forms in the center. I wouldn't doubt it if the iron nickel provided some type of permeability type effect, similar to like a transformer. When you have a wire loop and you have convective, you have currents flowing through that loop. If you place a piece of iron, the permeability of the iron is very high. So what happens is that it increases the strength of the magnetic field. So say it's weak, and you put the iron core in there, and then it gets really, really strong. And then it expands out a little ways. So yeah, you have your core, the global magnetic field will dominate. Meaning, this is also another predictive element of stellar metamorphosis. If you have a global magnetic field, chances are there will be no sunspots. Meaning, red dwarfs that have, well, once they have the global magnetic field dominate, the formation of sunspots will stop. Sunspots will start. They will go away. There will be no sunspots on brown dwarfs. Now, say sunspots, I guess they're not sun-related, they're related to these, but no magnetic activity that can dominate that global magnetic field, because the global will dominate any kind of surface activity. So it'll make it a lot calmer, so to speak. So a lot of that heat and energy will dissipate and move towards the center, as well as it'll continue radiating away in the radiation belts. But basically, that's it in a nutshell. As well, keep in mind that you have brown dwarfs, and you also have Jupiter has a strong field, and then Saturn has a strong field with his rings. And you have Neptune that has a field too, and Uranus has a field, and Earth. And the only time that the magnetic field dies completely, the global magnetic field dies, is when the star ceases any kind of internal motion. Because, the remnants, meaning the ability of an iron nickel core to keep a magnetic field isn't very high. So once the convective motion in the interior of the star, when it starts solidifying completely and it's very, very, very old, like Venus is, then the magnetic field completely dies. There's no magnetic field at all, and then it's subjected to the radiation belts of hotter host stars and solar wind of hotter host stars and that kind of stuff, and eventually, sterilizes the surface of that object. So if we're going to be looking for life, we have to pay attention to actually how big it is too, because for objects that are a bit smaller, chances are they don't have enough fluid motion in them to sustain the magnetic field. I would expect life to be in the water world / Earth a little bit later after Earth stages, but anything smaller than Earth, I really don't think there would be any real life, because it doesn't have a protective magnetic field around it. Everything would get radiated. So yeah, there you go. Go ahead and I'll link these two things to the bottom of the page. Also, you can look this stuff up yourself if you want to. There's probably some more up-to-date information concerning them, but hopefully this is a good overview to understand that the global magnetic field evolves with the star itself. And I know what a lot of mainstream people are thinking, well, the sun becomes a red giant. I don't know where they got that from. Okay.